In this section, we're going to start looking at propositional logic. Propositional logic will bring us up to the contemporary use and understanding of logic, which has departed quite markedly from the categorical syllogisms that we've been looking at the last few sections. In fact, if you were to go on and do advanced symbolic logic or to look at any journal of logic and logical studies today, most of what we are doing over the next few sections would be what you would find in those texts. So let's get started. Propositional logic is an advance in the logic of categorical syllogisms, which dominated until the 19th century. The advantage for propositional logic is that it can more easily translate the sentences of everyday language into symbolic form, and from there determine whether the arguments expressed in everyday sentences are logically valid or not. As you'll recall from the categorical syllogisms, we had to put categorical syllogisms into their proper form. Had to have a major, middle, and minor term. You were basically kind of limited to the two premises and the conclusion, connected by a middle term. And so it required a lot of sort of gymnastics to get sentences into the proper form. And we learned about some of the techniques to do that: conversion, obversion, contraposition, and so on. In the 19th century, Frege, Russell, Wittgenstein, a number of other important philosophers began to develop what has come to be called propositional logic. And you can pretty much take an average sentence and translate it into logical or symbolic form. And from there, through what we will look at as truth tables, you can analyze the argument and determine whether it is valid or invalid. So how do they go about translating everyday sentences into symbolic form? Well, the key component of this process is what's called logical operators. And the core of propositional logic is a simple statement that is either true or false. Now, you'll recall that we already talked about this earlier, that a statement is simply that which is true or false. But what propositional logic does is it looks at longer, complex sentences as a combination of simple statements. So if I were to say, for example, that Jeff Bell is a Californian philosopher, that could actually be separated into two simple statements. Jeff is a Californian, and that is true, and Jeff is a philosopher, and that is true. And so what propositional logic does is it reduces sentences to their simpler components and uses logical operators to connect and characterize these statements. And so by the use of operators and connectives, complex propositions and claims can be expressed in terms of symbols. So usually a letter is used for characterizing the simple statement, and then the operators connect these statements. So if we made C for Jeff is a Californian, use just the letter C, and P for Jeff is a philosopher, we could simply connect C and P with an operator that connects or conjoins two statements. That operator is what's called conjunction, which you can see in this table here. We have 5 operators. The first is negation. So if we had this, what's called the tilde, the negation sign before a statement, so if we had that before C, right, Jeff is a Californian, it would mean not C, or it is false that Jeff is a Californian. So that would be how that would be translated into symbolic form. The conjunction, if we were to say Jeff is a Californian philosopher, it would be C and or dot. Dot will be the way that you have it in the text. So the dot is the conjunction. So C and P would be Jeff is a Californian philosopher. The disjunction is the wedge, and that's either you will pass or fail the class. So that's the disjunction. The conditional is the horseshoe in the text. Sometimes it's a single arrow like we have here. And the conditional is if then. If you study, then you will pass. And the biconditional is an if and only if statement. And it's either symbolized by a double arrow with the head in both directions, or as in our textbook, the triple bar. The triple bar is, in our text, how the biconditional is symbolized. So let us take a simple statement, Jeff is a Californian. This statement is either true or false. That happens to be true. If one were to deny this claim, they would use the tilde operator, the negation operator, to deny the claim. So if we symbolize the statement, Jeff is a Californian, by the symbol J, let's say, then to deny this claim, or to say that it is false, that Jeff is a Californian, we simply symbolize it as follows: not J. So that would be true of any statement. And you can put the tilde or the negation outside any long or complex statement. As we will see in exercises in this chapter and chapters to follow, that you'll have the tilde or the negation outside very large, complicated statements, where you'll have statements within parentheses, and these parentheses themselves connected by other operators, in turn within brackets, and then the tilde or the negation outside the bracket as a whole. And what that tilde or the negation basically does is it turns something that was true into false, and something that was false into true. So it flips the truth value. Okay, so let's go on and talk about the other operators. If we want to express two simple statements together, we conjoin them with a conjunction operator, the dot. The statement, Jeff Bell is a Californian philosopher, is really two statements, since one of the two can either be true or false. These two are Jeff is a Californian and Jeff is a philosopher. Either one of these can either be true or false. They both happen to be true, so the conjunction, J and P, happens to be true as well. As we will see later on, if either of those two are false, then the conjunction is false. If I'm not a Californian, then it's false to say I'm a Californian philosopher. If I'm not a philosopher, it's also false to say I'm a Californian philosopher. So it's only true when they are both true. That'll be something we look at later when we look at truth functions. So, as we say, to summarize, it may be true that Jeff is a Californian, but false that he is a philosopher, or vice versa, or they could both be false. Okay. So, moving on, some statements are expressed in the form of exclusive disjunctions. For example, one can say that you will either pass or fail this class. If you didn't fail, then we can say you passed. If you didn't pass, we can say you failed. The disjunctive operator is used to express such statements. So P or F can be used to translate I will either pass the class or I will fail the class. And if we happen to end up with a statement that says not F, meaning you did not fail this class, then we can conclude P, that you passed the class. That will be something we will look at later on as one of the argument forms, the disjunctive syllogism form, as we move along in looking at arguments and validity with respect to propositional logic. Many other statements are expressed as conditional statements. For instance, I might say to my class that if you study for this class, meaning read the text and do the exercises, then you will pass. The implication operator, or horseshoe, is used to express these compound statements. So S horseshoe P, or S implies P, can be used to symbolize the compound statement, if you study, then you will pass. Okay. The most difficult of the operators to understand is the biconditional, which is used to express an if and only if claim. So a biconditional is equivalent to the following: P implies Q and Q implies P. So we can see the two conditionals, or biconditional, here. For example, if one claims that a presidential candidate wins the presidency if and only if they win the Electoral College, one is simultaneously saying both that if they win the presidency, then they win the Electoral College, symbolized as P implies E, and if they win the Electoral College, they win the presidency, symbolized as E implies P. The triple bar is used to express these biconditionals. So P triple bar E expresses the two conditional statements at once. Now, not all conditional statements are biconditional. For example, if I say you study, then you will pass, S implies P, I'm not necessarily saying that if you pass, then you studied. It could have been an incredibly easy exam, or you might be incredibly smart, cheated, etc. If I say you will pass if and only if, often expressed as if with two F's, If and only if you study, then the two conditional statements are implied. So with these operators in hand, we can now translate sentences. And almost any complex sentence can be expressed in terms of operators just discussed. You'll be required to translate some sentences into symbolic form, but we will quickly move on from this to simply dealing with the symbolic expression of compound statements. And the translation part is just simply to remind you and to kind of remember that all this is ultimately rooted in statements that people make and assert about the world. And the symbolic translations are in order to analyze the logical relations and the validity of the arguments, which is what we're going to spend most of our time over the next few sections doing. So let us take the compound statement, Tommy Hilfiger celebrates casual if and only if neither Ralph Lauren nor Calvin Klein offers street chic. This can be translated as follows. So one of the things to look at in this statement down below, as I have it translated, is what's called the main operator. And the main operator is the main thing that connects the two statements, or the main thing that we look at last when we're determining the truth value. And so in this particular case, the main operator is the triple bar. So the statement Tommy Hilfiger celebrates casual if and only if, that's the key operator here, neither Ralph Lauren nor Calvin Klein offers street chic. So this neither nor is a disjunction, but it's a disjunction that's negated. So we have the negation sign outside the parentheses at the R or C. Now this leads us to a very important topic. As you can see in the text, there is a distinction between what's called well-formed formulas and formulas that are not well-formed. And the basic idea is this, that any two statements have to be conjoined by some operator. So for example, in these instances, we have the statement A and B. There's no operator connecting these two statements. There has to be an operator there, so it's not well-formed. The A and then immediately followed by parentheses B implies C. There's no operator between the A and the B. A parentheses is not an operator. We either need a dot or a disjunction or a horseshoe or the triple bar. We need some operator to connect these statements. And similarly, everything within a parentheses counts as its own compound statement. So the last example, A implies B in parentheses, and then B or C in parentheses, that's basically two simple statements next to each other. That's just like AB. We need an operator between the two. So that's not well-formed either. So the way to put these in a form that is well-formed would be as follows. We put A dot B is well-formed, A or B implies C is well-formed, and A implies B and B or C is well-formed. Another example, here we have a case where we have operators between each of the statements, but we have three statements without knowing which ones we should deal with first. As in math, we have what's called the order of operations, and you need to determine the truth value of in a particular order. And the way you determine the truth value is you first figure out what the main operator is, and then you figure out the truth value of the non-main operators first. Well, in this A implies B or C, we don't know what the main operator is. And so we didn't know how to go about determining the truth value, because the truth value would differ if we had the parentheses around the A implies B, and then it would be disjunction C, would be different than if it were A implies and the parentheses were around B or C. And the same is true with the next example of A and B triple bar C. So the truth value of these compound statements would differ depending on which order we go about determining the truth value. So as a result, these are not well-formed formulas. So what we need to have for them to be well-formed is parentheses, so we know what to do first. So in this case, we have A implies, and then in parentheses, B or C. So the main operator here would be the horseshoe. Now if we had the parentheses around A implies B, then the wedge, the disjunction, would become the main operator. And then we would then determine the truth value of A implies B, and then the truth value of the main operator. This will become clear in a minute after we talk about truth functions. And then the other example, A and B within parentheses, triple bar C, it now becomes a well-formed formula. Okay, probably the most important thing that we'll be learning with respect to propositional logic that largely sets the basis for everything else we'll be doing in the rest of this class is what's called truth functions. As you'll recall from the very beginning of this course, logic is dealing with the preservation of truth from one statement to another. So in a valid argument, the truth of the premises is preserved in the conclusion. So true premises lead to a true conclusion. And so in order to deal with logic, we have to have truth values of statements. So a statement has to be, as we have seen, either true or false. Now, with the conjunctions and the operators that we have been looking at, the logical operators, there are some interesting truth results with respect to these operators. And that's what the truth functions has to deal with. And so you can see in this chart here, and there's a chart in the textbook as well in the inside cover. It's an important thing to remember. After you do a number of exercises, you'll probably remember all these. But just briefly, I will point out what's going on in this table, and then I'll go one by one through each of the operators, and we'll look at the truth function for each. But we have P and Q, and we have two statements, and because there's two statements, there's four possible truth values for these two statements. P can be true, Q can be true, P can be true, Q can be false, P can be false, Q can be true, or they can both be false. If we had three statements, we would have 8 potential truth values for those three statements. If we had 4, we would have 16. Now, we're not going to go 4. You won't be having to deal with 16 lines of truth tables, but you will have to deal with 8-line truth tables. We'll see some examples later on in the exercises and in later sections. But for the time being, with two statements, P and Q, there's 4 potential truth values. And so this table shows all the potential truth values for each of the two logical operators, each of the logical operators. So in P and Q, as you can see, the conjunction is only true when both P and Q are true. And we could see that already, right? That's Jeff is a Californian and Jeff is a philosopher. Jeff is a Californian philosopher is only true when it's both true that I'm a Californian and true that I'm a philosopher. The disjunction is true in all cases except for when they're both false. The implication is only true when the consequent is false. And the biconditional is only true when either both P and Q are true or both P and Q are false. Now, what we will do is we'll discuss these so you can understand sort of the reasoning behind this chart, how we end up with these results, because it might not seem intuitively obvious at first. So let's first go to negation. Negation simply reverses the truth value of a statement. So if P is true, then not P is false. Fairly straightforward. Conjunction. In P and Q, a conjunctive statements are only true when both statements are true. So we've been looking at this one a fair bit. If I am neither a philosopher or from California, then the claim that I'm a Californian philosopher is false. Okay, now the disjunction. Disjunctive statements are only false when both statements are false. So for instance, take the example of either J.K. Rowling or Drew Brees is a novelist. Again, the keynote app is auto-correcting Drew Brees to a possessive, but you and I all know we're talking about Drew Brees, the quarterback. So take either J.K. Rowling or Drew Brees is a novelist, or either Tom Brady or Stephen King is a novelist, and either J.K. Rowling or Stephen King is a novelist. In each of these three cases, the disjunctive statement is true since one of the two at least is a novelist, right? Okay. Only when they are both false is the statement false. So either Drew Brees or Tom Brady is a novelist is false because neither one is a novelist, and so the compound statement is not true and is false. So I think that clarifies disjunction. Conditional. Remember, conditional, it is only false if the antecedent is true and the consequent is false. In all other cases, the three other cases, it is true. Okay, this one seems a little non-intuitive, but let's understand it this way. Think about under what circumstances you would think I was lying if I said that if you got an A on the final, you will get an A for the class. Or, let's symbolize that as F for A on the final implies A in the class, C. So F implies C, okay? If it's true that you get an A on the final, and true that you get an A in the class, you would say I told the truth, right? If it is false that you get an A on the final, and yet true that you get an A in the class, would you not say I lied? Though you would not say that I lied, right? You'd be happy, but you wouldn't say I had lied to you. And if it's false that you get an A in the class, A in the final, and false that you get an A in the class, you'd also not accuse me of lying, okay? Only if you get an A on the final and don't get an A in the class would you then accuse me of lying. So that's the only circumstance in which you would say I was saying something false. Okay, so the biconditional. Recall the biconditional statement is true only when both statements are either both true or both false. So to get a sense of this, recall our earlier example. A presidential candidate wins the presidency if and only if they win the Electoral College. Okay, so we could say Trump won, that should be won with a W. Trump won the Electoral College, and it is true that he won the presidency. So we can see that this is true. Okay, so it's true that he won the Electoral College, and it's true that he won the presidency. So the Trump won the presidency if and only if Trump wins the Electoral College is true. But it is also true if we say that Hillary Clinton wins the presidency if and only if she wins the Electoral College. Both sides of the triple bar are false. She did not win the presidency and she did not win the Electoral College, and yet the statement as a whole is true. It would be true to say that Hillary Clinton only wins the presidency if and if she wins the Electoral College. And both sides are false, and yet the statement as a whole is true. So this is what's called truth tables, and so this now allows us to determine the truth of propositions, compound propositions. And so that's where truth tables for propositions comes in. So we can use truth tables to evaluate the truth value of propositions of any length and complexity. Okay? So for example, using an example from the book, let us take A, B, and C to be true and D, E, and F false, and evaluate the following proposition. Okay, not, okay, the tilde or the negation sign outside the parentheses, C or not A, implies not B. So the main thing to look at is, what is the main operator? The main operator is the horseshoe, right? Because it's not within any brackets or parentheses. The only time the tilde or the negation sign is the main operator is when it's the only thing outside brackets and parentheses. Any other time, it's going to be the other operator that's outside brackets and parentheses. That's the main operator. So in this case, it's the horseshoe. So what we will do then is we will determine the truth value of what's in the parentheses first, and then what's in the parentheses is negated, and then that will flip whatever the truth value is within the parentheses. And then after that, we then determine the truth value of the implication or the main operator, and that will give us the truth value of this proposition. So let's plug in the truth values, right? A, B, and C are all true, and D, E, and F are false. So we have no D, E, or F here, so they're all true. So we have true or not true implies not true. So we have the negation signs for these two instances of true. So let's flip those because that's what the negation sign does. So we have true or false implies false. Now, the disjunctive proposition, remember, is only false when they're both false. So we have one true, one false. So we could say that it is true, but it is negated. So we have not true. So we have false implies false. And for the implication, and a false implies false, it is true. It's only when true implies false that the whole thing is false. In the exercises, you'll have some more longer and more complicated propositions to analyze, but this is basically the way you go about doing it. We can also use truth tables to classify statements. So, for example, a tautologous statement is always true. So no matter what truth values you put in, the final truth value will always be true. A self-contradictory statement is the opposite. No matter what truth values you put in, the final truth value will always be false. And lastly, in contingent statements, which is usually what we deal with in everyday life, the truth value of contingent statements will sometimes be true, sometimes false. So you'll have at least one true or false result in the truth tables. You won't have all one or the other. So let's give an example. Here we have an example of a truth table, and what I'm doing here is simply laying out all the possible truth values for G and H, right? We have two different statements, G and H, and so we have 4 possibilities, right? Remember, if we had 3, G, H, and I, we would have 8 possibilities. So, but the way to do this is you take the first letter, if we have 4 possibilities, so we divide it in half, so 2 true and 2 false. And then we divide it in half again, and that'd be 1 true, 1 false, 1 true, 1 false. If we had 8 lines, we'd have 4 true and 4 false, and then divide in half 2 true, 2 false, 2 true, 2 false, and then 1 true, 1 false, 1. So we basically go dividing in half until we end up with 1, 1, 1. So we're alternating back and forth. So in this line of 4, we have true, true, false, false. And then H is true, false, true, false. And then we have the conjunction with G within the brackets. And then the main operator is the horseshoe. So let's kind of go through these examples. So T implies T in the very first line, gives us a true truth value. T implies F gives false. False implies true is true. False implies false is true. Okay, so the second column here gives us the truth values of the compound statement within parentheses. Okay, and then G, we plug in the same truth values from before, T, T, F, F. And we combine that, and we do the conjunction operator with the truth values on that second column. So T and T is true, false and true is false, true and false is false, true and false is false. So now we have the truth value of the conjunction, which is outside the parentheses, so that's the main truth value of what's within the brackets. And so we use these truth values to determine the main operator, which is this horseshoe with the H. And the H, we plug in the same truth values from before, TF, TF. And so that gives T and T is true, F and F is true, F and T is true, F and F is true. So in this case, all truth values are true. So this is an example of a tautologous statement. If we ended up with it all false, it would be self-contradictory. And if one of them were true or false, then it would be a contingent statement. Now we can also go on and compare statements, okay? So logically equivalent statements have the same truth values at every line of the table. So like the second line is true in one, and it's also true in the other, and all the other lines are false. If it's the same, then it's logically equivalent. Contradictory statements, they have the opposite truth value at every line of the truth table. So where one statement has it as true, the other one has it as false. If at every line of the truth table we have that, the statements are contradictory. Consistent statements are true in at least one line of the truth table. If I am consistent in what I say, then what is true in one circumstance should also be true in another. Okay, so if we think of a politician, in the famous Lincoln-Douglas debates, Stephen Douglas accused Lincoln of being inconsistent, of saying one thing in northern Illinois, in Chicago, and something else in southern Illinois. So in northern Illinois, let's say in Chicago, he would say, I am opposed to slavery, appealing to the anti-slavery sentiment in the city. But in southern Illinois, he was accused of pandering more to the slave interest and say, I'm in favor of slavery. So if it is true that he's for slavery in one statement, but false that he's for slavery in another, then he's not being consistent, right? If he were consistent, if he were saying he's against slavery, he would be saying it in the North as well as in the South, okay? If he's not saying the same thing in the North and the South, then he would be inconsistent. Inconsistent statements are statements where there is no line where the truth values are true. I'm being inconsistent if what I claim to be true in one circumstance is not true in another. So let's take an example. Take K implies L and not L implies not K. And we do, the truth values, let's do the first one. We have two, so we have 4 lines. So T, T, F, F, T, F, T, F. And so T implies T is true, T implies F is false, false implies true is true, and false implies false is true. So the bold underlined is the truth value of that operator for that statement. And then we do the next one, and we keep the same truth values for L, so TF, TF, but then it gets negated, so it becomes false, true, true. And then we have, keep the same truth values for K, T, T, F, F, but then it gets negated. So we have F, F, true, true. And so we do F implies F is true, true implies F is false, false implies true is true, true implies true is true. So this column of bold underlined truth values gives us the truth value for this statement. As you can see, they are the same at each line of the two statements. So these two statements are logically equivalent. Okay, so you now have enough to go on and do the exercises in 6.1, 6.2, and 6.3. Do review the reading and the text very carefully, and watch this video again if you need to, and then go through the exercises, and then afterwards then you can look at the exercise video to see if this helps clarify things where there may need some further clarification. Good luck.